All right, gang, 5500. Sorry for the abrupt ending in the previous video, but I knew it was going to take a while for me to get more papers, so I just thought let's just end it and create a new video for this. So what I want to look at here is just inference for beta 0. Makes sense if we looked at inferences for beta 1, we would look at for the intercept as well. Go ahead and tell you, I'll take a little different approach here. We know the answer. The answer is 1.288. To 1.830. All right, so let's see how that was found. First of all, beta 0 is the estimate B0 is the estimate for beta 0, and B0 is really easy to find. Just take the mean of y minus the beta 1, and I've already found it. So B0 found above, so B0 is going to be already calculated for us. All right, so that's where we're going to build the confidence interval. It turns out that beta 0, the distribution of the beta 0s is also normally distributed with the mean beta 0, and the standard deviation, or the variance, actually turns out to be the mean square error times 1 over n plus the mean squared over the sum of the deviations. So the test statistic t would be equal to still our estimate minus the hypothesized value, which would typically be 0 over the standard deviation. Now, I'm not going to illustrate that. What I do want to illustrate is I want to take a look at the confidence interval. So if I were to calculate a 95% confidence interval for beta 0, here's what I would need. The first thing I'd need the mean square error, which I already have. And then I just need to be able to manipulate this. I'm going to do this in pieces. So I'm just going to, I don't even know, I'm going to call it part 1 because I'm just not in a creative mood, I guess. I'm just going to take a look at this part right here. So 1 divided by the length of ACT plus mean of ACT quantity squared I need to divide that by the sum of the denominator. Part 2. Feel goofy calling it that. The mean square error times the part 1. So I need to take the square root of part 2. And this will be the SD for beta 0. All right, so the standard error is going to be 0.138. Now, if you're paying attention, you notice that for the intercept that the beta zero that we calculated using y bar minus b1 x bar is the same thing as the estimate. It should work out that way. Be pretty silly if it didn't. And the standard deviation for b0 is equal to the standard error. If I calculate the test statistic, I would get an extremely low p-value and a relatively high t-value. Now, the t-critical will be the same. So I'm just going to calculate the 95% confidence interval. So again, the estimate is 1.5587 is, yeah, okay. I don't know why I got messed up. And then the T critical is 1.963344 times the standard deviation for beta 0. Well, I did something really silly here. Yeah. So you can see the 1.2877 and 1.826 corresponds when we calculate it as what R gives us for the confidence interval. So let's go on to some other things. And this is going to be a little bit more involved. Not much. We really, I mean, I don't know if we ever really get too deep in 5500. 6500 gets a little crazy, but 5500 stays pretty tame. What I want to do now is I want to switch gears to interval estimates. Of the expected value of a y sub h. Let me, this is kind of bugging me. Do a little house cleaning here. Okay, you know, I don't think I'm going to need this, so I'm going to delete that. I'm going to go full screen here. Okay, now, common objective in regression techniques is to make predictions. And my doctoral advisor, I remember many years ago, told me that, or told the class, that, you know, regression techniques are used to make predictions, whereas ANOVA techniques, which you'll learn from me if you take my 6610 and 6620, they explain relationships. Now, it all meets out there with the general linear model. It all meets out there somewhere. But depending on the goal of the project, the statistical technique, if you want prediction, regression technique is for you. So if in the example that I just closed, we had that x was equal to ACT and y was equal to college GPA. So it may be of interest to come up with a predicted mean college GPA. Maybe an admissions director would be interested in predicting the mean college GPA for, you know, higher ACTs, like maybe 32s, versus maybe lower ACTs, which would be 18 or 19. So a little notation. Let's establish right now that x sub h is a level of x at which we want to estimate the mean y. So I think of this as x sub h is from our sample, or it is another value in the scope of building our model. In other words, it's not a new observation. And this is really critical, that you can distinguish between the two. There I am sloping to the right again. Let me tell you the difference. If we're choosing an x sub h from our sample as something that's really related, very closely related to the scope of building our model, versus a new observation would be where we build a model and then maybe an admissions director, a few months later has a student walk in and they want to use our model to make a prediction for that particular student. So for these problems, we're actually predicting a mean. For this type of problem, for a new observation, we're actually predicting a particular value. The variance is going to be a lot larger for these than it will these, but we'll cross that bridge once we get there. So kind of drum roll, please. The predicted value for y at some h value is just found by doing exactly what you would think it would be, just plugging in the value of x sub h into our model. Now, just as before, we want to think about what is the sampling distribution of our y hat sub i's. Well, what would they, and again, it reminds us a lot of any sampling distribution, right? And specific to the one we just looked at with B1 in one of the previous videos. So in other words, we're asking ourselves, what would the y sub I at that h value look like over repeated samples? In other words, holding x constant. Well, the theory shows us that the distribution will be a normal distribution, but with getting ahead of myself, let's just go ahead and make this clear. With the expected value of y sub I, and the variance will be the mean square error times 1 over n plus x sub h minus the mean squared. Notice this is not summed, but we still have the sum of the deviations in the denominator. Sum of the deviations for x seems like it shows up everywhere, doesn't it? Now, a couple of questions, 3 questions. Do we have normality? And if so, what do the mean and the center, or I'm sorry, the center and the spread look like? Well, it turns out that we do have a normal distribution, because our y hat sub i's is a linear combination of our y sub i's subs before. So if we know if our y sub i's are normally distributed, that any linear combination of a normally distributed variable will create a normal distribution. The mean will be equal to, well, not equal to, but the expected value, if we will, of the y sub hat h. All right, stop being a robot and just putting down what I write. Think, what should go next? What should go next? Now, if we were in class, I could call you out, but we're not in class. So I would hope by now that you know that that would be next, which is equal to the expected value of B0 plus, it's hard for me to see, the expected value of beta 1, which is just precisely beta 0 plus beta 1 x sub h. Telling us what? Nothing fancy. We just, to get the expected value for the predicted value at a level h, we just plug in h sub h into our model. Now, the variance, I'm not going to prove this one. I'll be perfectly honest with you. I'm not sure I can prove it on the fly. Maybe. I don't know. Again, I'm going to repeat that. Notice no summation there. Why do you think I'm repeating that? Well, I bet someone's done that before, right? Now, some weirdness here that the variance is actually not going to be constant. The variance is going to be different depending on the value of x that we choose. And this provides a little bit of statistical craziness. So it's even kind of hard to explain. So the variability of the sampling distribution of y hat sub h is it's impacted by how far our x sub h is from our mean. So if that that difference is larger, then the square is, is actually going to be larger too. Let's do this. All right, so I've got some, we got this population we're drawing from, and we pull out a sample and we get a model, and then we throw our information back in and we pull out another sample. And we pull out another sample, and I'm just not going to keep drawing lines. But anyway, we know for sure that these all regression models will pass through the mean of the x and the mean of the y. As we move, if we choose an x sub h very close to the mean, notice that we're not going to get a lot of variation in our samples. Similarly, if we choose an x sub h right here, we're not going to get a lot of variation because it's closer to the mean. However, as this x sub h moves further from the mean, you can notice that we get more variation in the predicted values from. So anyway, that's what I'm talking about. I think, honestly think that the illustration does a lot more to make that clearer than does me, trying to speak it through. So, a test statistic would look like this. So we would have our predicted value of y at the particular x sub h minus the expected value of y sub h over, of course, the standard deviation of our y hat sub h's. Turns out that we lose 2 degrees of freedom, because again we're making these calculations based on a beta 0 and a beta 1. Now, this expected value up here will depend on what we're actually testing. If we're testing that the mean response is equal to 3.2. So let's say we're focusing this on an ACT of maybe 30, and we're predicting. I'm sorry, an ACT of 30. We're predicting a GPA. So we want to hypothesize that the expected value will be 3.2 at this particular set constant level of an ACT. Then it would go would be 32. If we were just testing that the mean is not equal to 0, similar to what we did with beta 1, then we would just have a 0 there. So it just depends on what we're testing. Now, what I want to focus on, though, is the confidence interval. And I want to illustrate one of these for you. Now, let's we know that a confidence interval is going to consist of 3 parts, right? Our estimate, our t critical. Well, it doesn't have to be a t critical, but we know that the t distribution. Well, I don't know if you know that, but I'm telling you that is the model, the probability model, and then of course here the standard error or the standard deviation. So confidence intervals are going to have 3 components. It turns out in this that we're going to use the predicted value of y plus or minus our t critical, degrees of freedom equals n minus 2 times, of course, y hat sub h. So let's make a prediction.